When it comes to the world of big data, you've got some pretty big companies doing a lot of things with data. Tesla has sensors all over their cars, and they're tracking billions of miles worth of data every single day. You've got companies like Palantir that are working with supply chain logistics and healthcare, taking across
Yep.
billions of points of data every single day. But the problem is, Alex, a lot of this data just isn't useful. A lot of it is just white noise. So in the next 10 years, when we have 100 billion connected devices all producing trillions of points of data, how do you think the world is going to deal with this?
I think you're spot on. That's a massive problem. And a lot of that data gets processed only to be thrown away. So imagine the energy footprint, the computational power, all of that fancy data science that has to go into data just for no output. Today, we're going to be talking to a guy named Jerome Nadel. He's the CMO of a company called BRAINCHIP. And what they do is, instead of doing traditional machine learning, they learn how to separate good data, as in data that provides real insight, from noisy data, so that all of the computation that gets done behind it adds real value. Before we get into it, I think we have one more announcement, right?
Yes. So this was a really, really interesting podcast, and we hope you all listen. It's a bit technical, but it also dives into a larger mission of what BRAINCHIP is trying to do. The special announcement is that in the next 2 weeks, we are starting this podcast, The Catalyst, on a brand new channel. And the reason for this is, quite frankly, we really want to build an audience that just cares about The Catalyst in one place, so that you don't have to deal with just Alex's content or my content, but you can go to The Catalyst to actually get your Catalyst content. Lots of fun interviews, lots of shows with me and Alex duking it out about different topics. So that channel will be in the link in the description, and it will be the pinned comment. We have one more video coming out on this channel in another week. And then right after that, August 1st, we will be on a new channel on YouTube.
Yeah, I'm super excited about the reception the Catalyst has gotten. I'm excited that we've been able to catalyze so many awesome conversations already, and I'm excited to breathe new life into it on its own channel, coming soon in a couple weeks. So with that in mind, let's jump into the interview.
Let's get into it. Hope you guys enjoy.
Let's get into it.
All right, everybody, welcome back to the 4th episode of The Catalyst. We are here with our second guest on this podcast. A really, really special guest. We're very, very excited to talk to Jerome Nadel, the CMO of BRAINCHIP, which is a very, very interesting company. We're going to talk a lot today about edge AI, IoT devices, and a lot of different things that have to do with that type of technology. So, Alex, we're going to tee you up for our first question, and we'll let Jerome start talking.
Sure, yeah. I'm an Internet of Things fanatic, and the big trend that I've noticed is that the Internet of Things is getting bigger and bigger, more and more connected, and everything has data, right? Even the watch on my wrist right now tells me way more than the time. It tells me about my health. It tells me about my sleep. It even tells me about my mood. So my first general high-level question for you is, what do you think about the Internet of Things and the amount of devices that are connected today, and the general trend towards all sorts of technology coming online?
Great question. Great lead question. And great to be here with both of you. Thank you very much. So, I think the hype curve of IoT is a little bit behind us. There was an expectation that the world was going to change, that computers are miniaturizing, and we would have at the edge, the fence of IoT, new capabilities. And in fact, that has happened. But a way to simplify the view of IoT is it's really about sensors at the edge, sensors capturing data. Or from an experience perspective, the way, as you just said, Alex, that we interact with technology, the way we interact in the physical world with digital is simplified through the inclusion of sensors. We no longer are tethered to a keyboard to enter information into some black box. We gesture, we speak, we pass by, we're recognized. So this notion of a blurred line between the analog physical world and the digital world through time is going to sort of move more Minority Report-like. And we're seeing it happen already. An iPhone today has 7 sensors in it. The watch that you just spoke to has a set of sensors. A 2022 car has about 70 sensors in it. So the big theme that we've seen over the last decade to two is the inclusion of sensors in digital devices to simplify the way humans interact with digital. And I think the next thing that we're going to see is these sensors become smarter. And they're going to become smarter through inference close to the sensor, through edge AI, if you will. And we'll break that down. That has 2 components. There's going to be a component of learning and training, and there's going to be a component of inference. When people think of AI, they liken it to cloud type AI, or from a learning perspective, deep learning, where inference and learning at the edge is much more basic, is more human-like, and doing simple inference of things that we see, hear, feel, etc. And to break this down, to simplify it, the notion is that if we can take the data coming from these sensors and quickly classify or do basic inference close to the sensor and just pass the answer forward, we're not polluting the pipes with unnecessary data. So in close on this first big question, we are coming to the point where IoT is no longer a buzzword. I think it disappointed because we hyped what everything would be, but in truth, the propagation of sensors in everything digital is happening. And now what we're seeing to really go to the next level is making these sensors smarter and moving to an architecture where we're efficient with how we capture sensor data, we analyze it close to the sensor, and we pass forward only what's needed.
So it sounds like the big shift here is away from sending all the data that you can collect back to the cloud for analysis, including analyzing a lot of noisy data that may not have a lot of insights in it, to being able to do more smart calculations nearer to the sensor. So for example, in the case of my smartwatch that we both mentioned, it would be more like, instead of connecting to an app on my phone that then sends things to Amazon's cloud, it's like having a chip right by the sensor doing all the calculations for my heart rate, for my exercise, or for my sleep, instead of sending the raw data and sending it to the cloud. Is that a fair assessment of the difference?
Well articulated over here. And I think as well, you talk more about the inference. So your watch is capturing, some sort of biorhythmic data associated with you. So it's capturing it, and it could stay local and do that inference local. The other side of that is learning. So when you're doing like object classification, it's this, that, or that. Or when you're looking at your heart rate or some biorhythmic data, there's a parameter of normality. And then when you exceed that based on an average range that it's interpreted, it's going to set some sort of alarm. So essentially in that device next to the sensor, if there were AI, these models are basically, they've been learned. That's the machine learning part. Now, when you talk about deep learning, the algorithms that support the categorization are more complicated. And typically they go up to the cloud. So take your iPhone for recognizing your face, and you're doing the multiple. You need to be connected, because at a security level, you want to make sure that it's differentiated you, because it has access to all of your secure detail versus anybody else. So that's a case where the learning is really happening at the cloud level, but the ability to say, I see you on the learned pattern is happening at the device. So there are going to be times when you need to leverage learning in the cloud versus learning at the device. And there are going to be times when the inference will actually be connected to the cloud. But our view of really edge AI is, to the extent possible, you need to do all the inference on chip in device. And even if you already have a model that has a set of classes, you should be able to add to that without having to go back to the cloud. So, a distinction here again is there are complex machine learning, deep learning that would be cloud involved, and there are more basic inferences connected to sensors that ought to be separated. And that's what we're advocating, is a lot of approach of edge AI has been sort of a scale down of cloud AI. And that works to a given level. But if you take a completely alternative approach of how you capture data, focus on what's essential, do the processing of that, and pass the inference metadata forward, it's radically, orders of magnitude more efficient. And it coexists with the notion of cloud AI. So they're both good, but they're different.
Sure.
This stuff is really, really exciting. Big data analytics, machine learning, AI. We know these are buzzwords and buzz terms, and they get thrown around a lot. And actually understanding the use cases and how companies like BrainChip are differentiated, I think are really important to understand. So kind of two questions that I think you can take on at once. You mentioned that the inference metadata is the sort of like key variable that needs to go to the cloud, and it has a lot of effects on the environment and all these other things that actually makes it more efficient. Can you explain some of the vertical use cases that creates the market opportunity for BrainChip to actually succeed? What are those cases that only need the inference metadata that your chips will be able to solve? And then you mentioned neuromorphic computing, which is a chip that kind of mimics the brain, which is the whole point of BrainChip. At a high level, how is that different from the other processors, and what is that market that you guys are trying to expose?
Okay, let's take them in reverse. I'll answer the second one first. Okay, so imagine you're sitting in a park looking at a lawn and you see sort of kids out in the field playing. If you could think of perception as a camcorder that's always reviewing and processing everything that's going on. But actually, we are a remarkable sampling system. And what we do is capture a scene and then look for the notion of events, look for the notion of change. And then we process that change. So imagine in scenario A, I'm continually computing to look for every dynamic variable in that visual array. And in the second, I'm saying, I've already captured a frame. Let me look for something that's different. So categorically different approach. And neuromorphic really is the latter. It's saying that I'm going to look for events that are then translated, sorry for the language, into spikes. And these spikes will correspond to the processing that I'm doing. So classic AI computing is referred to as convolutional, that you're going over and over and over in math matrices. Spiking neural networks say, I'm event-based. I'm going to look for change, and I'm going to process on that. So there's one theme of, do you need to capture and process everything, or can you just process what is, quote, essentially important?
So for example, Jerome, real quick, if you're in the park and you're doing this camcorder metaphor, and you're seeing a girl who's riding a bike and she falls down, is that theoretically a spike? Because that stands out, and like that's something that you're going to categorize more than just the regular stuff going on in the park?
Sure, we look for anomalies over here, and anomaly detection is that sort of thing. So again, we would be burnt out if we're just having to hyper process everything. So we're so magically efficient at saying that was different. So you start out at a sensor level by saying, I know I can capture everything, but there's going to be some sensor pre-processing, post-processing software. Here's a sensor that is smart. It cancels noise, it amplifies signal, and then we're going to get it and say, okay, using this, we're going to focus on the region of interest. We're going to use this event-based to process that. We're going to come out with an answer. It's a this or a that. It's in threshold, it's not. You said this, not that. And we're going to pass that, again, inference metadata forward. Now, that inference metadata can go up to the cloud, or it could stay within system. So let's take automobile, for example. You have multiple sensors that are all capturing data, and they could either, once again, pass all of that data forward to a localized central processor for processing, or they could do the processing close to the sensor and send that inference metadata forward. So architecturally, in an in-cabin, I open the door, I get inside and sit down, and it says, I've detected a person. I've detected you. You said something. I see it's you. You've gestured. So any of these actions are happening because a sensor has detected that behavior. I talked about a 2022 car having 70 sensors. Look at an autonomous vehicle where it's not just the vehicle itself, but its interaction with sensors outside and the communications that are going back and forth. And it happens when I describe it like that, it's pretty remarkable that you have all of this happening in real time. When you think discretely of all of the capture and computational activities that are occurring, almost in parallel, this is the future. This is now to the future. We don't need big data to do basic inference.
So I think this architecture is really worth exploring and talking about, right? Basically, what's being advocated for here is, imagine you have a Tesla that has both radar and cameras, just for argument's sake. So in the first case, the radar is collecting lots of data, the camera is collecting lots of data every second, right? Hundreds of pulses per second on the radar and 30 frames per second on the camera.
Yep.
When you connect that to or more, right? So when you connect that to a chip, that chip has to process all of that data. You know, maybe the radar's smart enough to like limit its noise, and maybe the camera's smart enough to like ignore camera flickers. But long story short, all of that raw data is getting processed by the same chip that's trying to put it all together in time and then make some detections, like this pedestrian that's crossing the street in front of me. You know, it's in these pixels of the camera. The radar says it's about this far away, which means I have about this much braking distance before I would endanger them, or so on, right? In the second case, the sort of architecture where we do more computing at the edge, what would happen is the radar passes information to, for example, a brain chip or a chip right behind the sensor. Instead of saying, here's everything I'm seeing, it would let you know when an event takes place. A light turns from red to green. A pedestrian crosses your field of view, so on and so forth. And now the amount of data that's getting back to the chip behind all the sensors and the chips behind them is only dealing with events or small pieces of data that would change the state of the car. Like, now I see a pedestrian in front of me. Now I see the light turn from red to green. Is that a fair assessment of the difference between those two architectures?
You know, it's an appropriate oversimplification, because it's
Sure.
not that I'm completely turned off. You know, there are going to be interim states, but fundamentally, the inference that's being captured is the data, the metadata that's being sent. To your point, Alex, when you look at a system as you described it, you could imagine that the implementations at the sensor are really basic, and they are really event driven. Was there something meaningful? Let me capture it. Let me do the inference processing and send it forward. And when I send it forward, there would be a receiving computation that would be more complicated and require more compute, but we would be part of that system as well. So architecturally, you know, we are connected to the sensors and we're connected to the receiver to do the processing. And if you take a systems view, we're saying that receiver is going to need so much less compute because you've already done a lot of the work at the point of capture. And then, you know, you get into the notion of inference performance, right? You're going to have false positives, you're going to have false negatives. And what you try to do is optimize the inference performance to a given level that is optimized against the amount of compute and the amount of power. So people designing chips come to us and we work with them to optimize the implementation. What are the boundaries that I'm looking for the inference performance, for the amount of compute, die size, and power? We tune that and against our architecture and then optimize that for a given use case, which is very different than when you have a chip that's already a product. It's like an ASIC, is an application-specific integrated circuit. It's designed for a given thing, and you might be able to tune it a bit, but you don't have the flexibility of saying, how do I want to use this now? You know, just to sort of blow our own horn, when you look at the performance of these inferences, so again, if you looked at all knobs and you max them, you'd want the inference to be high, you'd want the compute to be low, you'd want the die size to be low, and you'd want the power to be super ultra low. And we check the box across all of those. So it's not like you're giving up inference performance for power. We're able, with this architectural approach, to do both. However, let me caveat, some AI models are very complicated. Deep learning models, when I'm trying to speak in natural language, that typically is being done through machine learning in cloud. In this case, you might have a host CPU and you would just offload to do the AI acceleration to us. So there are times when we're going to fit as a component in a system where we're just taking the humble task of hardware offload for acceleration. And there are other times when the models are more basic, most of the cases out on the edge where you don't need all of that hardware. We can do it all.
From a following up from an architectural perspective, you've explained kind of the idea behind the chip and the architecture of it. Can you talk a little bit about how do you know if the performance of the chip is going well? Like, is it a question of if it's faster, if it's more efficient, if it has a lot of false flags? Like, what exactly lets you know this product is ready to go to market? We can guarantee this to the client that this thing is going to work and they should pay for it.
Is it by use case? Yeah, great question.
Great question, definitely. So typically firstly, do you have a network? And a network is like a cord, not a node, because a network means you've got a model and you have data. And then we're able to run the data on the model on our hardware and determine the performance. Is it getting it right? How long did it take? What's the latency? What was the power used? And these become key determinants over here. And again, when you look at like electric vehicles, obviously things like battery management and transmission are the big things to solve to enable a car to go further on a charge. But every milliwatt of power in that moving electronic capsule becomes meaningful. But I think, again, we shouldn't, miss the forest for the trees by just looking at one model, one data set, how did it work? We need to step back, and what we try to encourage is a roadmap of sensor inclusion. And, Alex, this is the move to IoT over here. We start with a sensor, a set of them. We keep adding more. They fuse together to do magic, and they do it, again, performantly with extremely low power.
That's a really, really interesting way of thinking about things. When you think about traditional processors, you're thinking about clock speed, instructions per second, whatever. It's so interesting to think about a scalable chip that can change depending on whether you care more about optimizing for power or optimizing for false alarm rate or optimizing for a wide number of use case specific metrics. Can you talk a little bit about a couple of the use cases that you've seen work extremely well in this paradigm and just compare how a brain chip enabled sensor would be able to do things versus a non brain chip enabled one in the same use case?
Sure. Remember, so let's just step back and talk about that continuum from cloud or data center AI versus edge AI. By definition, cloud means a lot of power, a lot of memory, a lot of data. And by definition, edge means exactly the opposite, right? And the scale down approach is to say, I don't need so much processing. Let me do this more efficiently, where again, I leverage sensor post processing, for example, and then I capture and compute in a more efficient way. So for us, when we're looking at these use cases at edge, remember that you're focusing on regions of interest and you're using this neuromorphic approach to look at events or spikes and process on them. And that's going to yield sufficient inference with way less power. That's really the takeaway. And the driver has been when you're at the edge, you're not plugged in. And power becomes the primary determinant of good. But neuromorphic has also been looked at. Intel and IBM have initiatives that are more research-based that are looking at how would this work in cloud. And the founder of BrainChip, Peter Vandermeide, a brilliant guy, as a researcher, as a sort of theoretician, believes that there could be application to data center for neuromorphic as well. It's exciting to see, as they say, rising tide floats all boats, that Intel and IBM have research initiatives on this, provides a level of validity. As others have come into the space, but primarily focused on a chip solution that supports a modality. We do vision in neuromorphic, and we have a discrete chip that will make your vision-based system work better. We're processor and sensor agnostic and have demonstrated that it works across all of these sensor modalities. And it provides that scale up, scale down, as you acknowledged, to say I could start with one and then add others in. But it's really like building a home. You're starting with an architectural plan to say, I know that this home is going to satisfy, my growing family, if you'll accept that metaphor, which I'm well beyond. I'm already a grandfather. So the growing family is not going to happen for me directly.
So that was great. And by 2030, explaining the use cases that you talked about, by 2030, following up on that, there's going to be about 100 billion connected devices. So there's going to be a lot of devices that are using these potential chips and different variations of it. How do you think we should be thinking about the market from a business perspective up until 2030? Do you think like connection speeds are going to matter, data size, device ecosystems, more and more use cases at the edge that we can't even conceive of right now because it just doesn't exist? Like, do you see the major market opportunity for BrainChip to capitalize on markets that potentially don't even exist and that theoretically you guys might even have a monopoly on if you have the best technology in the world for it?
Yeah, two ways to answer that. Michael Dell recently at an event was saying that by 2025, 75% of the world's data is going to come from the edge, from sensors at the edge. Whoa. 2025. Remind us, we're in 2022. So, this is happening. And we could sort of not be observing it, but clearly we're capturing, Alex, your watch and beyond. We're capturing this data and it's moving around over here. So let's step back and take sort of a strategic marketing viewpoint. For me coming into BrainChip and looking at the ecosystem of relevance for us with sales and our leadership team, we were whiteboarding out what are our key customers today. And again, as we provide an architectural design that goes into chips, that go into products, the obvious targets for us would be those that make chips, those that design chips on behalf of others, and large OEMs that have enough volume and budget that they're actually making their own chips. And of course, you both see a trend towards well-known companies taking that on themselves. So that's a target-rich base. And we would call those, without any judgment, sophisticated customers. And we're encouraging, and we have licensed customers in the chip design, the chip manufacturing, and OEM space. So that's sort of the inner years of our strategic plan. And imagine, if you will, in this diagram that's top right. But in the bottom left, and again, without value judgment, you have simple customers. And they're saying, I have electrical digital products that I could make better with sensors and AI enablement. And they're not looking to design their own SoC. They're looking to purchase in their BOM, in their bill of materials, a discrete component that will enable this type of AI. The inner years for us are definitely supporting and advocating to the designers and chip manufacturers to take this on board as a standard component, because they're going to be the ones that are supplying the simple customers. So where today a lot of our engagements are with sophisticated OEMs that can go through the evaluation cycle, have product planning generations out, and are already getting ahead of their competition. That's how they stay ahead. The ultimate big market is going to be the simple customers, because every device that is digital will have sensors in it, and every sensor will be AI enabled. This is not only an exciting entrepreneurial venture, but is good for the planet. This is a big movement, and I just find it just hugely compelling and exciting to be part of.
Yeah, I think taking that step back is really important. One thing that I think a lot of businesses sort of fail to ask is, just because we can sense it doesn't mean we should. What's the value added of adding this extra sensor or, looking at this extra signal? And I think you're speaking to a really interesting thought experiment over the next 10 years, as we get more and more sensors and everything, and we're getting this data deluge as a result of all data everywhere all the time on all things. I feel like a solution like this becomes more and more important to clean up as much of that data, provide as much value as close to the sensor as possible to sort of limit the noise that gets sent back, both literally and sort of metaphorically, from the edge to the cloud. Have there been any sort of data streams that you've come across that really surprise you or that really engage you, a use case that really excites you that's kind of coming down the pipe in the future?
That first part of sort of good for humanity, of this approach is real, and that we're coming to this sort of asymptotic point of no return. We have to revisit our carbon footprint, and it used to be don't burn oil and the like, and now it's as you've articulated, look at all of this noisy data and the pipe that we're filling, and let's be more efficient and mindful. So the birth of the cloud was amazing again, and the idea of new models of memory, even the notion of in memory or near memory computing to reduce latency. It's almost like memory and compute were free, and everybody got drunk on that and ran towards this is the new world. It's not. It's finite. It's limited. And when you're not in the cloud, when you're not at the data center with unlimited racks and you're out at the edge, you've got to think of this differently. And again, Alex, to the point you made, the pipe between the two. So really at a global humanity carbon footprint level, we need to raise visibility to that this is all amazing, that these sensors are blurring the line between physical and digital, and the way we walk through space and time is going to be a blur between the two. But we've got to do it in a way that's efficient and sustainable. I think not in a dystopian animal farm way, but I think in the future, and we have it today, that we have a chip in a device that is identifying, authenticating, and permissioning us as we walk through space and time. And probably we'll get to a point where there is some form of embedded device. And the convenience that will provide is, I don't have to tap on a turnstile to get through. I don't have to tap to pay. Everything will happen automatically. And this will be no more than, fundamental identification, authentication, and then permissioning to services around us. And I think the sensor world that we're already in, but moving toward, is really going to operate on the, let me identify, let me authenticate, let me permission. And these three things are going to be the blur where everything around us, you could call it XR from an augmented perspective, is going to come because sensors surround us. So there will be more data and the requirement, of course, for more security to make sure that the way we interact, is pure and respectfully private and all of that sort of thing. It's happening. So I get in my car and it's personalized around me. I gesture, I speak, I'm recognized. We're already on the way there. The big issue is going to be how we manage authentication and permissioning, which is a little bit beyond the AI discussion, but it connects to it as well.
So basically you're saying BrainChip is going to control the metaverse.
That's what I heard.
Be a humble enabler of the metaverse. And I think, what's really exciting about where BrainChip is that BrainChip has done a really good job. There's a tool called MetaTF that takes, if somebody has existing, what are referred to as convolutional neural networks, and they want to use a spiking neuromorphic framework, we do the automatic conversion of that. So you could take what you've already worked on and put it through, our washing machine, and it comes out the other side ready to be put into a neuromorphic framework. And I think making that onboarding easy, making this technology easy to consume, is clearly important to get it adopted. And that's really, what we're trying to do is to promote this. Rising tide floats all boats, seeing again the Intels and IBMs of the world investing heavily, us being a commercial leader with a viable in-market offer is an exciting place to be. And we just need to keep up with, the advocacy for this approach and show it working. And that's what we're looking at for our near-term future.
That's awesome. What an exciting future. I'm excited to follow along the BrainChip journey. I definitely am excited to see how the IoT trends we talked about shaped out. And I'm definitely super excited to see what kind of other use cases your chip designs are going to be used in the near future.
I would love to stay in contact and do this again. You were both great. Thanks so much.
Sure.
Thanks so much,
Thank
Jerome.
you.
That was awesome.
So I'm really excited about the future of IoT and connected devices, and I want to say a huge thank you to Jerome Nadel and the team at BrainChip for making this interview possible. That was really awesome, and I hope you got as much value out of that as I did. What do you think, Amit?
Yeah, the things that he mentioned around what it means to have true artificial intelligence, or what they call essential artificial intelligence, to actually make sense of the data that we're getting and the implications that that has for climate change and companies and how they can actually make meaningful interpretations of the things that they garner. It's going to be interesting to see what happens over the next decade. And it was really fun to talk to a guy who's at the cutting edge of this type of technology.
For sure. Yeah, I'm super excited about the future. And speaking of the future of this podcast, just a reminder, next week will be the final episode of The Catalyst on ticker symbol U, and after that it's moving to its own separate channel.
Yeah, the next week's episode is going to be a fun episode. We hope everyone tunes in to July 27th episode or the final episode of ticker symbol U's main channel Catalyst content. And hopefully it will catalyze us into an entire new world onto the new channel. So we hope you guys join us on July 27th. It's going to be a special episode.
Thanks for watching this awesome interview, and we'll see you in the next one.
Bye, guys.